Going to take a closer look at phase changes. Now, we learned this at the very beginning of the year. Phase changes are physical changes. There are no chemical bonds broken. So remember, if we started with H2O as a solid, so we're talking about ice, and we melt it into H2O liquid, see, nothing changed about the chemical composition. It was H2O and it's still H2O. But during these phase changes, what is happening is that intermolecular forces are being broken. In the case of water, the intermolecular forces are hydrogen bonds and dipole-dipole forces, and of course, dispersion forces. Again, when liquid water is vaporized to gas, those remaining intermolecular forces are broken, and then the molecules just kind of fly off into the gas phase, and they're not sticking to any other water molecules. All right, now, this is a water molecule, so see the H2O, the oxygen is bigger, it's more electronegative, it has a slightly negative charge. That hydrogen has a slightly positive charge, and this dotted line, this represents the hydrogen bonding between different water molecules. So during a phase change, this is what's broken. These hydrogen bonds are broken, and then if in the case of melting, then the molecules in the liquid state can now have some new movement, and in the case of a gas, the water molecules just completely vaporize. So changes of state and phase changes are just physical changes. All right, also, boy, you should know this after the labs we've been doing this week. Temperatures do not change at a phase change. So we saw when we were freezing something that we could identify the freezing point by a temperature plateau. And the same is true for all temperature changes, for all phase changes. The temperatures do not go up, they do not go down, they stay the same. But energy is being added at these phase changes. Energy in a heating curve is being added, but the kinetic energy remains the same. When our temperature remains the same, kinetic energy is the same. So what's that energy doing? It's not changing the kinetic energy, it's not changing the temperature. Well, that energy is breaking the intermolecular forces in the case of a heating curve. If we were actually cooling something down, it would be organizing the molecules by forming intermolecular forces. So, anyway, there is no temperature change and no kinetic energy change during a phase change, but energy is at work. Okay, heat or enthalpy of fusion. All right, so this is a new term for us. And you can think of enthalpy as heat, and enthalpy's, enthalpy's abbreviation is an H. Enthalpy's definition is heat under constant pressure, but all of these systems that we're talking about now in phase changes, we're not changing the pressure. And so you can see things called heat of fusion or enthalpy of fusion, and really the difference is enthalpy is under constant pressure. All right, so delta H, and then they abbreviate fusion FUS. Now the definition of the enthalpy of fusion is the change that occurs at the melting point when a solid melts. So a lot of people don't like that word fusion in there, but that's what it is. The units are joules per gram, and for water, the heat of fusion is 334 joules per gram, and that's in your reference packet, and I think it's on page 1. Okay, so in other words, to melt 1 gram of water, you have to supply 334 joules of energy. Now, sometimes you'll see this word latent out front of the heat of fusion or the enthalpy of fusion, and it's the exact same thing as the heat of fusion. Latent just means that our temperature is not changing, so don't let that bother you if you see that word. Okay, so let's just go ahead and do a problem. All right, you have got 25 grams of ice, and you are at the melting point. So you're right at 0 degrees, and they would like to know how much heat is required to melt that. Okay, so we're going to use 25 grams, how much we have. It takes 334 joules to melt 1 gram. And so all we do is we multiply these together. The grams cancel and we're left with joules, and we get a pretty big number. We get 8,350 joules. So if you had 25 grams of ice right at 0 degrees, it would take 8,350 joules of heat to melt that ice. Now, let's see. There was something I wanted to tell you here. Well, you may see an answer in scientific notation, and that would be 8.350 times 10 to the third joules, or an answer might be reported in kilojoules, and it would be 8.350 kilojoules. So what you do is you take your heat of fusion and then you multiply it by the amount in grams, and you will come up with the amount of heat needed to melt that piece of solid. All right, now what if we're going the other way? What quantity of heat is released when 44 grams of liquid water is at the freezing point and it freezes to ice? Okay, so we're right at the freezing point. The only difference here is that it's asking what quantity of heat is released. And actually this is important. When something is freezing, it is releasing heat. And when something in the previous slide is melting, it is absorbing heat. So if you've got 44 grams of your water, we're just still going to multiply it by the heat of fusion. And the only difference is in this freezing, we are releasing heat. We are releasing heat. So 44 times 334 joules per gram. The grams cancel, and woo, we're getting a bigger number here. 14,696 joules is what my calculator spit out, but I want 3 sig figs, so it's 14,700 joules, or 1.47 times 10 to the 4th joules, or 14.7 kilojoules. These are all the different ways to represent the same thing. Gracie is over here wanting petted, so I'll try and do both. Okay, so here we go. So water is freezing here, and it is releasing heat. Okay, so if we've got a solid, and then if it melts to a liquid, that's endothermic. Heat is going into that. But if we got the liquid and it's going down to the solid, and this is energy, so it's going, lower in energy, then the heat is being released from that water to the system or to the surroundings. From the system to the surroundings. Okay, so there's something else. It's the heat or the enthalpy of vaporization. It's oh my goodness, this should have said vaporization. Okay. It's delta H VAP, vaporization. This is the enthalpy change that occurs at the boiling point when a liquid is vaporized. Its units are also joules per gram, and the heat of vaporization for water is a lot higher than the heat of fusion. It takes a lot more energy to convert liquid water into a gas water than to just melt it from a solid to a liquid. Kind of makes sense because, here you're going from a liquid to a gas and you're pretty much completely breaking all those intermolecular forces. But anyway, this is in your reference packet and it's listed as 2,260 joules per gram. All right, so again, you might see the word latent out in front of it. Don't let that word bother you. And let's go ahead and just use the heat of vaporization for a problem. All right, calculate the amount of heat necessary to vaporize. We have 50 grams of our liquid water. And we are right at the boiling point, so there's no delta T here. And it takes 2,260 joules to vaporize 1 gram of liquid water. So we've got 50 grams, and so we're going to multiply the heat of vaporization by our mass, and we come up with 113,000 joules. Let's practice our scientific notation. 1.13 times 10 to the 5th joules, or let's practice converting to kilojoules. That would be 113 kilojoules. Okay, So there you have it. When you are at a phase change, when you are at the temperature where something is going to change phases, the temperature doesn't change. So delta T, is 0. So what we have are these things called the latent heat of fusion or the latent heat of vaporization. And you just multiply that number, which will be given to you, by the mass that you have. And that's the amount of enthalpy or the amount of heat that is either required for the process to happen or the amount of heat that is released when the process happens. Okay, well, we're going to combine this with the MCAT equation, and we're going to have just a really fun time solving problems. Have a good night.